Welcome students, 5th chapter I am up and down and round exercise 5.4 solution. Use Baudhayana Pythagoras theorem to show why theorem 6 must be true. This is theorem 6. A chord of a circle having same length are all at the same distance from the center of the circle. Look at the diagram. Here given is the chord length are equal given. In diagram AB is one chord that is equal to GF is another chord. This is given one. These two lengths are equal. The chords of having same length is given. Next, to prove here, what to prove means same distance from the center of the circle. So from the center of the circle, for the chord A, C is the distance from the center of the chord. For chord GF, CH is the distance. So we need to prove these two distances are equal. But we should not use any concurrency concept. We need to use Pythagoras theorem. So let's take the chord AB first. So in chord AB, that is proof. For the proof, first I am going to take chord AB. In chord AB, CE is perpendicular to AB. We can see that in the figure. CE is perpendicular to AB is given. That implies E is the midpoint. When the center to chord, a perpendicular line will divide the chord into two equal parts. So E is the midpoint. AE is equal to EB, which is equal to half of chord length AB. This is for one chord. Take for another chord. Our another chord here is GF. So in GF, in chord GF, CH is perpendicular to GF, which implies GH is equal to HF is equal to half of GF. That is for next chord. Now both the based on the chord we will take one triangle. For chord AB I am going to take a triangle AEC. For chord GF I am going to take a triangle CHF. Use Pythagoras theorem. So Pythagoras theorem, right angle is there means opposite is the hypotenuse. Opposite of right angle is hypotenuse. So in AC is the hypotenuse. So AE squared plus EC squared is equal to AC squared. You know very well, from the center to any point on the circle is nothing but radius. So AE squared plus EC squared is equal to R squared. We will consider this is our first equation. Now for the next chord, same way, if we are taking triangle CHF, CF is the radius. So CH squared plus HF squared is equal to CF squared. So CH squared plus HF squared is equal to R squared. This is our next equation. When comparing 1 and 2, both the right hand side are. So on comparing 1 and 2, right sides are equal. So we can equate our left side. AE squared plus EC squared is equal to CH squared plus HF squared. Here we have to prove CE is equal to CH. Here I wrote EC. Now what about AE and HF? Our AE, look at here. AE. Our AE is equal to half of AB squared. At the same time, our HF is equal to half of GF. So when we are analyzing that, what we got? Our AE is equal to half of AB and our HF is equal to half of GF. and given condition AB is equal to GF. So these twos are equal. Now AB, half of AB is equal to GF is given condition, means half of AB is equal to half of GF. Half of AB is AE, that is equal to half of GF is HF. So that we can cancel AE and HF. AE squared and HF squares are equal, because AE, we got AE is equal to HF. Then, so we will be getting CE squared is equal to CH squared. So CE is equal to CH. So when the chords are equal, the perpendicular distance also equal. We proved without using any concurrency concept. Using Pythagoras theorem, we have proved. Second question, consider the figure 5.15 if CE is perpendicular to AB. The chord AB, CE is the perpendicular and CH is perpendicular to GF and CE is equal to CH. The perpendiculars are equal. Show that AB is equal to GF. So here given condition is the perpendicular CE is equal to CH. We need to prove the chords are equal. AB, previous sum, the chords are, this is converse part of theorem 6. So here they didn't mention anything. So using concurrency itself, we can prove that. So for the proof, we will take the triangles, two triangles. That is in triangle ACE and triangle CHF. These two triangles, what is given? Perpendicular to AB. CE, this is also given condition we can take. CE is perpendicular to AB and CH is perpendicular to GF. These are the given. So here in this triangle AC is equal to next triangle CF, because radii. And next angle CH, angle ACE. First triangle we took AEC, no? So angle 90 degree, which is 90 degree, AEC is equal to angle CHF. Both are 90 degree, that is given. Because they are perpendicular, that is given. And another one more condition given, very important one, CE is equal to CH, that is also given. The perpendiculars are given. So triangle ACE concurrent to triangle CHF by what criteria? We got one hypotenuse. This is our hypotenuse. 90 degree, 90 is here and AC hypotenuse here and one of the side is given. So by RHS criteria, both the triangles are concurrent to each other. By CPCT, we can say AE is equal to HF by CPCT. Then what about our given condition, that is E is the midpoint. So if E is the midpoint, E is the midpoint means AE is equal to EB, which is equal to half of AB. Otherwise AE we can take as AE is equal to EB is equal to half of AB or half of AB, or else we can take twice AE is equal to AB. Same way, H is the midpoint. H is the midpoint, which implies GH is equal to HF is equal to half of GF, or we can say twice HF is equal to GF. So, if AE is equal to HF means twice AE is equal to twice HF. So, replace this. Twice AE is nothing but AB, that is equal to twice HF is nothing but GF. So, the chords are equal in length. If the perpendiculars are equal, then the chords are equal. Next, for the same question without using concurrency, again using Pythagoras, we need to prove this. Again, once again, here given condition is CE is equal to CH, and CE is perpendicular to AB, and CH is perpendicular to GF. This is given. We need to prove AB is equal to GF. So, for the proof, we are going to take chords, two chords. We are going to consider two chords and Pythagoras. We will check the Pythagoras. In chord AB, CE is perpendicular to AB, which means applying Pythagoras, we will getting AE squared plus EC squared is equal to AC squared. So, AE squared plus EC squared is equal to R squared. This is our first equation. Equation number 1. In chord GF, CH is perpendicular to GF. So, 90 degree at H. So, CF is the hypotenuse. CH squared plus HF squared is equal to CF squared. CH squared plus HF squared is equal to R squared. This is second equation. On comparing these two, on comparing 1 and 2, right hand side equals, so we can equate left side. AE squared plus EC squared is equal to CH squared plus HF squared. Now, what is given condition? If CE is perpendicular to AB, CE is perpendicular to AB means our AE is equal to BE, which is equal to half of AB, and CH is perpendicular to GF means GH is equal to HF is equal to half of GF. Now, we are having AE. AE is equal to half of AB, and our HF is equal to half of GH. So, AE is equal to half of AB, which implies twice AE is equal to AB. Here HF is equal to half of means twice HF is equal to GF. So, we can cancel which two? AE and What about the given condition? See, CE is equal to CH. These two are equal because that is given here. CE is equal to CH. So we can cancel. We will be having AE squared is equal to HF squared. So AE is twice AE is equal to AB. Twice AE is equal to, so AE is equal to HF. If we are multiplying both the side 2 times, 2AE is equal to 2HF. So replace 2AE is equal to 2HF means twice AE AB and twice HF is GF. So the chords are equal. Without using concurrency concept, using the Pythagoras concept, we proved this. Thank you.